Can see. Let me share again. Can you see anything, Sakura?
Just see like a blue block saying that you have started screen sharing, and that's it. I can't see like the
But you
actual.
can see us moving.
Yeah, I can see like the
Oh,
camera.
yeah. Let me. Can you see now?
Yep, I can. Thank you.
Yeah, feel free anytime to use the mic. I want you to participate, so please jump in anytime. All right. Let's try. Good to see everybody. So this week we're going to finish spectral theorem for self-adjoint and normal maps. But it won't be tested, so I saw the midterm. It's only up to last week. So make sure you know your homework very well, all right? Review your homework well, very well. Important, all that stuff. What was this week? No, but what topics were in this? Yeah, know your inner products. But make sure you don't know what. All right. Any questions? There's a lot of Zoom people, so you guys can ask questions, please. All right, let's do the spectral theorem. Right, first we need to study the matrix representation of the adjoint. So yesterday we said that first of all, what is adjoint? just to remind you a little bit, not too. So, where is adjoint? So, the adjoint of a linear map is the unique map such that you have this relation. Okay, so it's like an integration by parts. Okay, you can, that's the adjoint. And for matrices, we have a specific formula that we can prove now. We'll prove that the adjoint matrix representation is equal to the conjugate transpose of the original map. So that's a very clean, nice representation. And if you like, that also gives you an idea of what adjoint is. So adjoint is basically, so how do you get these matrices? So you have T, V to V, you go down to gamma B, and then you go up. And then this is the matrix map. And what was our formula? T is right, gamma B inverse composed with Tm precomposed with gamma B. And what we're saying is T star is also that, right? T, Tm star. But then this is gamma B inverse of T and conjugate transpose gamma B. So in a way, we're not only giving you the matrix, we're giving you the adjoint. Because what do? You first, suppose you have a linear map, you find the matrix Tm, you take its conjugate transpose, okay, and then you use the coordinate maps to come back to T adjoint. Like let's say in practice, you want to find T star. You either do it the more proper way with the inner products, like we did before, right? So in the example here, you just start with from here and you go and you get a formula. That's the proper way, okay? But another way is using the coordinate maps, because you know what the matrix is. Like it's very complete for the adjoint. All right? Okay. I mean, you're not going to be tested on this. I'm just telling you as a advice, like, if you want to find adjoint. All right. Right, let's prove this. So you start with this matrix of T, and let's look at the kth column. So let me remind you what TE is. This guy is the TE1, TEN, right? You just have these columns of the EIs. And the way you find TEK, because they're orthogonal, you know the coefficients explicitly. So here's another, beautiful application of orthogonality. You know the matrix. You have explicit coefficients. All right. So in other words, the column. So if you go back to your matrix, it will be the kth column. It will be TEK E1. This is a number down to TEK EN. Okay. So if people ask you for matrix representation, you can just compute these projections. Okay. So that's another quick way to find matrix representation. Like you can go back to all your previous homeworks or whatever, and you can do it again with this, much faster. Right. But anyhow, so now you know what the matrix entry is, the IK entry. It's very specific. is this projection. And we will relate it to T star. So you play the same tricks, and instead of T, you put T star, okay? So now you have the IK entry of this, and you have the IK entry of that, and we're gonna compare them. Okay? All right. So let's do that. We start from the left. This is the definition. You take the adjoint first step. This is the definition of adjoint, that you can move it to the right. And then you use that inner product has conjugate symmetry. Okay, so when you flip the arguments, you have to pick up a conjugate. Okay, and my question is, can you tell me how to finish from here? Even Zoom people, feel free to, yeah. Do you know how to finish from here? Yes. So which matrix entry is this? Yeah, so this is the Ki conjugate, which is equal to what? Right. So this, let's call this matrix M. So we just got MKI and put a star here. Or, so then, yeah, this is MKI, which is equal to MIK transpose. And right, yeah, I mean, it goes back and forth, so you can flip them again. So call this guy A. So M is equal to A transpose conjugate. It's the same. Okay. Can go back and forth. All right, Zoom people. All right. Good. So that was the matrix representation of the adjoint. Let's talk about some of the properties. So you have linearity of the adjoint. Let me do it here, because that's the one we will need mainly. So yeah, V S plus LT star W is equal to S plus lambda T V comma W by adjoint, linearity, and what should the second part be? Any ideas what the second term should be? Yes. Lambda? Are you sure? Oh yeah, you're yeah, no, you're right. I don't know why I said that. I thought it was, I don't know why. Oh, I see. Yeah, it will come later. Okay, never mind. And then you do your conjugation again, your adjoint thing. Star W, and then okay, now let me ask you again. How to finish from here? Yes. No, wait, you can do it. Right, yeah. So because you write lambda as lambda bar bar, and then you have to bring it back in, so you lose one of the conjugates. So it would be lambda bar. get V S star L bar T star W. Okay? And how do we get that this is equal to this? What choice of V shall I take? Yeah, sure. Like what? No. So let me be more suggestive. You write V and then yeah, call this y2 y1. It will be y2 minus y1 0. And then this is true for all V, so take the difference. So then you get y2 minus y1 squared is 0, which implies that y2 is y1. So what is this? Okay? So this is a trick to show, to find the adjoint in general, right? Yes. No, it does, just I want you to know why. Instead of just writing it. Yeah. All right. Yeah, the other ones, I mean, we're not gonna use them really, so I'm just gonna mention them. So PT star is equal to T. Adjoint of the identity is the identity. What else? When you take adjoint of composition, it switches. So let me show you why quickly. So this is equal to ST VW and what do I want to say here? Actually, no, it's too long. I'll do it later. So if we have time, we'll come back to that at the end of the class. Because I have to make choices of B and W. Okay, so yeah, when you switch, yeah, when you take adjoint, it switches. Another result is that the kernel of the adjoint is perpendicular to the image of T, right? So you take some V in the kernel, and you take some TW, this is 0. So V is in kernel of T star. And I think it's easy to see, right? Because you just, let me do it another way. So take V in kernel of T star. So then you have, let's say, TWV, use the adjoint. But this is 0. Okay? So that shows that elements in the kernel of T are perpendicular to the image. Okay? All right. Yeah, this is another result that I have to leave to the end because we don't need it for spectral theorem. So there's a criterion for self-adjoint. It follows from the following that if TV comma V is a real number, and I think I have the formula here. So it basically follows from this identity, which you can check by hand, that the difference of TV comma V minus its conjugate, you can write this in terms of, you use conjugate symmetry first, and then you write this as T star. So this guy over here is equal to T minus star. Okay? Okay? And I mean, it's not immediate from here, but hopefully you can see it, that if this guy is a real number, what is this equal to? Yeah, because z minus z bar is 0 only when z is a real number. Okay, for z complex. Yeah, I mean, yeah, it's not really like, yeah, I mean, but once you see it, then you get this result, yeah. So, and then vice versa, if you have t equal t star, this is 0. So you can see how you can bounce between the two, okay? The proof is more involved than this, but I just want to give you the main idea, because we don't need it for the spectrum. All right, any questions? Yeah, let's move on. Okay, why do we care about self-adjoint? Because they are diagonalizable. Okay, so today we're going to prove spectrum theory. So T is equal to T star if and only if you can represent it as a diagonal matrix. And actually over a real and complex. So it works for both. So this is a stronger result. And on Friday, we're going to prove for normal maps a weaker result. But this is the strongest spectral theorem we will see in this course. Yeah. And the interesting, of course, is that every symmetric matrix can be written as a diagonal matrix. All right, let's go. First result you need, since you're working over, since you might be working over real inner product spaces, you need real eigenvalues. So let's prove that they are. Take any eigenvector. Right? And yeah, this is the identity. But you can also do it a different way. So this is easy, right? TV comma v is equal to lambda v, and then you use the norm. But then I think I did with the adjoint here. Oh, yeah, yeah, okay. So let me explain what happens here. So this is easy. Here you're just using the definition of eigenvector. Okay. Here, let me do a middle step. Here we're going to use the adjoint. We're going to use the following fact that if V is an eigenvector for T with lambda, so TV is lambda V, then T star of V is lambda bar V. Okay, so let me prove that here. So let's start from, let's see, let's do it like this. T star, let's put B for both. Yeah, V. All right, so we have TV, V. All right. Use the eigenvector. So lambda V. Okay. Take out the lambda. And can you tell me how to finish from here? Yeah. Yeah, you just put it back in. So you have V lambda bar V. And yeah. So you get your V T star V minus lambda bar V. No, because you don't even know what adjoint is. Yeah, because adjoint by definition is the guy through inner product. Yeah. Yeah, good question. Yeah, right. So you don't even have. It's kind of weird to think about, right? But there are generalizations, because in theory, the spectral theorem doesn't use inner products. It just says you can write your matrix in a diagonal way, right? It just says you have a matrix representation that's diagonal. No, this is for inner product spaces. Well, that's the assumption, but suppose you work in a more general setting where you don't have an inner product. No, there are results. That's what I'm trying to say. Yeah, this generalizes, but in the real world, you always have inner products because you have the dot product, and that's all you really need. All right, so you do this trick, and then right, but T star is, then you use the T star is T, and so that's how you get the first step, and then you use the TV is lambda B. Okay, which is lambda bar. So this is equal to this, but the same guy is equal to lambda bar squared. We take the difference. And this is for all V. V is a non-zero vector because it's an eigenvector. That's the only eigenvector we look at. So we get that lambda are 0, so lambda is real. Okay. If you have a question, let me know. Even chat, Zoom people, if you have a question, put it in the chat. I will go check there every 5 minutes. Okay. All right. Yes. So here's the pretty result that the characteristic polynomial of self-adjoint maps only have real roots. Okay, so we're going to do a nice argument using this, so make sure you understand. If you have a question about this, this is the key part. Make sure you understand this. All right, so what I'm saying is, you start with a self-adjoint map. You find that all its eigenvalues are real, which implies that the roots of P lambda are real. Okay, we're gonna flip this argument. So make sure you're comfortable here, because these steps are, some of these steps are reversed. Okay, so let's do it. All right. What's so difficult about real inner product spaces is that you do not have the fundamental theorem of algebra. Okay, that means it's not guaranteed that you have an eigenvalue. So let me remind you again, P lambda equal to the determinant of T minus lambda I always has at least one complex root. Okay, and that's a big problem for the real spectral theorem. For complex spectral theorem, we're just going to use this result and we're done. But here we are in a bit of a trouble that we need to prove the existence of a real one. Okay. All right. So let's see. This is a very subtle one. So we have our determinant, our characteristic. And we know that it has at least one complex root. Okay? So we know that. But going back to our previous argument, this same polynomial can only have real roots. So this is FTA. But the other one, where we wrote it as product of lambda I for lambda I real, This is the T star. So this equality forces lambda star to be a real number. Okay? That's the tricky argument here. That you already have a factorization of P lambda only in terms of real roots. And so you just compare it to the one from FTA. Yeah, but you don't know if they exist. So what it says here is FTA says roots exist. And from before we're saying, oh, they're real. Because the argument is reversible. So eigenvalues of T being real is if and only if P lambda has real roots. So that's we're using that this goes back and forth. So this is a very subtle argument. So, okay. So you go up to complex, you get your complex roots. These are roots, but roots are eigenvalues. And the eigenvalues can only be real. So the roots are real. Is that okay? If you have a question, you can tell me, it's fine. I see mixed looks. Some people get it. Maybe I should do a simpler example. How should I say? So P lambda says you can write this as lambda, lambda star, G lambda, where lambda star is complex. Results from last week show that this is equal to TV lambda star V. Okay? But TT star itself adjoint, and we just showed that this implies that lambda minus lambda star bar is equal to 0. So that implies that lambda star is real. Is that okay? I mean, if you have a question, you can just tell me, it's fine. All right, let's prove the speckle theorem. So we use the same induction argument, so this is a good review. So dim V is immediate. Why is it immediate? Just to make sure you're following. By the way, I want to say validity. Why dim V equal to 1 is immediate? Just to make sure you understand. So we're showing diagonalizability, right? Why n being 1 gives it immediately. Yes. Yeah, I know, because you always answer this. So I was looking at you as well. I remember you said this. You're like, why are you even asking this? kind of like. Right. But for now, we're assuming we're proving diagonal. And of course, the work is ahead of you because you have to prove diagonal in the induction step. So the base case has many directions. You're right. You can use this same base case to get upper triangular, to get diagonal, to get a bunch of things. That's right. So, but you're right. The meat of the proof is in the induction step. This is sort of doesn't have much content. At least it says on the base level is proof. Okay, so now induction hypothesis. Assume everything that T restricted W is diagonalizable as long as you don't have the full dimension. Okay, this is called induction hypothesis. Okay, everybody happy? Zoom people? And now here's where we're using the existence. Since you have at least one real eigenvalue, it means you also have an eigenvector V, where V could be a real inner product space. That's why this is difficult. Okay, we're proving it for real inner product spaces. That's what makes it hard. So anyways, because real inner product spaces means you only have real eigenvalues. You're not allowed to work with. So remember, we had this crazy guy. This guy is not self-adjoint. This theorem does not apply to it because it only has complex eigenvalues, plus minus I. Okay, so this is, yeah, but this guy is normal. So we're going to prove it on Friday that you can diagonalize, but over complex. All right. So take W to be the span of your eigenvector and take U to be the perp space to your eigenvector. Okay? So I have to prove two things to you. First, I have to prove that dim U is strictly less than dim V. And I also have to prove to you that T restricted to U goes from U to U. Okay? Well, because your induction hypothesis is for maps only restricted to U. Yeah. So you're proving the result over inner product spaces of dimensionless. Yeah, that's the tricky part. So you're not allowed to go to V. It has to match. And then you add one more basis vector and you group. Okay, so let's do one by one. Yeah, okay, I'll do this one first. Actually, okay, let me do this one first. So we have to prove this, that it preserves domain codomain. So in other words, I have to prove you that this guy here is 0. Okay? Why? Because it says that if you take a U in W perp, then TU is still perpendicular to W. Okay? In other words, TW perp is perpendicular to W. Yeah. I will still write this, I don't know. But yeah, let's do that. You take adjoint, but adjoint is itself. Oh, okay, fine, right away, right. But this is something we talked about. So since W is an eigenvector of T, you get that TW star is equal to lambda bar W. Okay, so that's step one. Then yeah, I have to finish from here. How do I get that this is 0? Anybody? Oh, wait. Yes. Yeah, perfect. Because yeah, because this guy exactly. So U is in W perp, right? And W is in yeah, because all right. So you preserve domain and codomain. And yeah, let me ask you this as well. Why do we have the dim perp is strictly less than dim B? Again, this is just bookkeeping to make sure you understand. Yes. Yeah, so since you at least have one eigenvalue, this is where the meat comes, right? you get the Dean W exists, so it's at least one. So you have at least multiplicity one. All right. And yeah, so let me ask you from here, how do we finish? What's the punchline here? Because I did it for upper triangular, so I just want to make sure you understood. It's the same argument. So what do we want to show? We want to show that there exists a basis B for V such that TB is diagonalizable. Okay? Or in other words, this is equivalent to yeah, that B is an eigenbasis for B. Okay, so I think this is easier. So yeah, can you show me why we get an eigenbasis for V? Using our induction hypothesis. Yes. With W be the U. Yeah, yeah. I mean, yeah, exactly. That's all there is to it. Yes. Yeah. Yeah. That's it. So it's even simpler than what I was thinking. So by our induction hypothesis, um, since Dean W perp is strictly less than Dean V, you can get some B tilde of W perp. That's an eigenbasis. Okay? But indeed, Dean V is equal to Dean W perp plus Dean W. Right? Remember this result? That W perp form a direct sum. Okay? And so then we take the basis of W, which is just one guy. Yeah, so then let B tilde to be, sorry, let B B tilde adjoint with union with W, the eigenvector, with the real eigenvalue that we proved the existence of. And, okay, and this is a basis for V from this dimensionality. Because right, so that's another way you can show basis very quickly. You get linear independence, and then just show that the cardinality matches the one of the space. Okay, because we proved that it's an invariant. That every basis has the same number of elements. Good. Yes. Right. So the way you perfect question. So I mean, just to be clear, though, here we're done because eigenbasis being a basis gives you diagonal matrix. So that was the, but in a way, yeah. So, but you can do this. because this is what the first block will be the B tilde stuff. So you have TU1, TUN minus 1, and the last guy will be the TW, right? But by induction hypothesis, this is lambda 1 to lambda n minus 1, and TW is equal to lambda star W. Okay? Oh, no, it doesn't work for any bit, like, how do you say this? Oh, yeah, of course, because you just, right, perfect. So in general, you have this result that C is equal to the change of basis from, so let me first write that. So you have to go from C to B, and then from B to C. Yeah, okay, so that's but then this guy is diagonalizable, so put the P diagonal P inverse PCB, and then group them together. So this guy is one thing, call it Q, and here you're taking inverses, so Q inverse. Okay? So, perfect question, yeah. Any matrix representation is diagonalizable, because you can just compose with the change of basis matrix. Okay? Good question. Zoom people? Okay. All right, so we proved the real spectrum theorem. But there are more than the self-adjoint maps. So we talked about the rotation matrix. This guy is not self-adjoint. So I will prove this in a second. Yeah, so here's some other maps that you still have a spectrum theorem. Okay, but you have to work over the complex numbers. All right. So these are the maps that commute with their adjoint. So we're not asking to equal their adjoint, we're just asking to commute with their adjoint. And it turns out that's still good enough. You still get diagonalizable. So every self-adjoint map is normal. Okay, so let me do this in more detail. TT star is equal to TT, which is then you flip it around, right? So here you go, you use self-adjoint, and here you use self-adjoint. Okay. So what's the implication about? Yeah. Anyways, the point is you have more normal maps than self-adjoint. Then you have Okay. So in theory, you could be normal but not self-adjoint. So the spectral theorem is not true for normal maps. We have to prove a new version that extends to the bigger family. Okay. So here's I think I do the example next, right? Yeah. Self-adjoint. Oh yeah, this is a simple. So take this map that flips the elements and puts a minus. This is basically the matrix 0, minus 1, 0. Sorry. Because you get yx minus x, y minus x. Okay. All right. And let me prove you that it's normal. First, I have to find you the adjoint. So we have txy, ab, and you take the dot product, right? So let me do the middle step. y minus x dotted with AB is equal to YA plus minus XB. Okay? Everybody happy? But then you group them together to get AB. So can someone tell me what's T star of AB equal to? Just to see if you follow the symbol. Huh? What's T star AB? Is it right? What? Yeah. Is that okay? Okay. So is T star self-adjoint? Can I get a? Is it? Yeah, it's not right because T of AB is equal to uh, BA, which is not equal. Sorry, to B minus A, which is not minus BA. So, for example, T of 1 is 1 minus 1, whereas T star of 1 is equal to minus 1. Okay, so so it's not self-adjoint. All right, anyway, too loud. Let me finish up here with the normal. So it's not self-adjoint, but you are a normal map. Okay, so you have that T star AB is equal to minus BA, which is what? Which will you flip it again? So yeah, and you can do the same the other way. Okay, so you are normal. All right, anyhow, I don't want to. We'll talk about tomorrow. Thank you. Right. Thank you.